Hey guys, we're back and ready to talk about our last topic in this section. Before we do, I wanted you to see that I ran out of my chemistry shirt, so I made my own chemistry shirt today. 2 Peter 3:10, one of my favorite chemistry-related Bible verses, and I'll just read that to you real quick. It says, "But the day of the Lord will come as a thief in the night, in which the heavens will pass away with a great noise, and the elements," what are we studying constantly in chemistry? The elements will melt with fervent heat, both the earth and the works that are in it will be burned up. And so even though if you look up that word elements there, it means something that's an orderly arrangement, something that's ordered like our periodic table is of elements. So maybe not exactly elements like we think about it, but the idea is still the same. And it just reminds us that God's in charge of this world, right? That this is the world that He's created, and He's the one that's going to end this world, and there's going to be a new heaven and a new earth wherein dwells righteousness, rather than the tainted version of life that we have right now that's been tainted with sin. And so I just like that reminder. I said whenever we started this class that chemistry is really a study of our Creator. It's a study of our God, because He's the one that invented creation and invented chemistry. And so I like that verse because it's a reminder that He's the one that's ultimately in charge, and He's the one that we need to always be. As we study all of these things, it needs to bring us back to our Creator. So just a quick topic today, I want to talk about activation energy. And what does activation energy have to do with? Well, if we, for a long time now, we've been considering chemical reactions. We've balanced them. We've done stoichiometric calculations based on the chemical reactions. More recently, we've looked at heat that's produced by it and figured out how much energy it takes to do a particular chemical reaction. But here's my question. If some of these chemical reactions, why don't we just see them taking place all the time? And the example that they use in the book is, for example, the combustion reaction of paper, right? And so when you have the combustion of paper, the chemical reaction is basically the paper, which behaves as the fuel plus oxygen, O2, and then that's going to produce the carbon dioxide and the water and the heat. And those are the products of that reaction. So if that's all you need for that reaction to take place, then why doesn't our book just burst into flames, right? Because we've got paper and it's connected with oxygen in the air. And so why don't all chemical reactions just happen all the time whenever those chemicals come in contact with one another? And the reason why is because of this topic of activation energy. All right, so activation energy, by definition, is the energy required to start a chemical reaction. So the reason that the book doesn't just burst into flames is because there's not enough energy, activation energy, to get that reaction started. Now, if we add heat to the equation, if we put a match up there, now we have added additional energy to that system, and guess what will happen? Sure enough, the paper will begin to burn, right? But you got to have enough activation energy in order for that to happen. All right, and so as it turns out, every reaction has to have activation energy. It's just that for some reactions, the activation energy is so low that you can just basically put the compounds together and they'll react. The reaction will take place. And we've done some experiments in class where that's happened, right? We just had to mix them together and all of a sudden the reaction took place. Well, it all has to do with how great or how small the activation energy is that's required for the reaction to take place. And so in order to examine that, we're going to look at what we call reaction coordinate diagrams. And I've got a couple listed here because I'm going to highlight the differences in these two, right? So this one just to kind of show you, just to break down what we have on each of these. And I'll show a picture as you're watching the video that's kind of a close-up of this so you can see everything a little better. But you'll notice that each graph has on the y-axis, if you will, if this is as an XY coordinate system, on the y-axis here we have energy, right? Energy in kilojoules, and it's broken down in units of 100 kilojoules, right? Same thing in the one on the right here, in the graph on the chart on the right. But on the bottom here for the x-axis, what we have is the reaction coordinate. And so what the point to that is, this is the axis where the reaction is taking place. So as the reaction goes along this way, these are the energy changes that are taking place as the reaction occurs. All right, and so these graphs, these reaction coordinate diagrams, will tell us what the activation energy is for a particular chemical equation. And that activation energy is this value right here. So this is the activation energy. Right? And so all you have to do to figure that out is basically look at the graph at the highest point, which in this case is 600 kilojoules, and subtract from that where the graph was when the reaction started. And in the case of this chemical reaction, it's 200 kilojoules. And so what this graph tells us is that the activation energy for this particular one is, it equals 600 minus 200, or 400 kilojoules, right? That's the activation energy for this system. Now, in contrast to that over here, and I'm just going to abbreviate this as AE, activation energy. For this graph, it's just 600 minus 500, right? So it equals 100 kilojoules. And so the point is that this reaction is much easier to get started, right? Because it only requires 100 kilojoules of activation energy to get it going, whereas with this one we need 400 kilojoules of energy. Okay, so looking at the graph will tell you, what the activation energy is. It'll tell you by comparison to other reactions how easy it is to kick this reaction off. Another thing that we can learn from this particular reaction is the change in H, and so that's what this value represents here. So the change in H is if you remember, it's the energy at the end of the reaction minus the energy at the start of the reaction, right? And so we have the energy at the end here, which is 200. So change in H equals the ending energy. No, I'm sorry. For this graph, my bad. The ending energy is 400. 400 minus the starting energy, which was 200. So for this particular reaction, the change in H is 200 kilojoules, right? Now for this reaction over here, the ending value is 200. So change in H for that one equals 200 minus the starting value was 500. So for this one, it's negative 300 kilojoules, right? And so what we know then, because the change in H for this particular graph is positive, then we know that this is an endothermic reaction, right? Where am I going to write that? We're going to say here, endothermic. And for this one here, because change in H is negative, this is an exothermic reaction. So in addition to telling us about the activation energy, these type of diagrams will also tell us the change in H, and therefore it will tell us if it's an endothermic or an exothermic reaction. So it's a diagram of the reaction as it moves along. We start off with the reactants over here on this end. We end up with products over here on this end, and then we can calculate those values, activation energy, and the change in enthalpy, right? The change in H. So we're going to do a quick problem, and that's all we'll have for this section here. And that's example number 14.4. And it's on page 429. And this particular problem is simply asking us to diagram, to draw a reaction coordinate diagram for the particular chemical reaction that they describe. And so they tell us this. In this chemical reaction, the reaction starts, the starting energy equals 100 kilojoules. And the activation energy, again we'll abbreviate as AE, is 500 kilojoules. And they tell us that the change in H equals 200 kilojoules. All right, so that should be enough information for us to draw the reaction coordinate diagram for this reaction. So we'll draw our two axes here, and we'll label this one energy. We'll say that's in kilojoules. And everything's, divisible by 100 here, so we'll just, we'll do 100, 200, 300, 400, 500, 600. We'll just put 200 here, 400, 600. All right, and down here we've got our reaction coordinate. In other words, this is the coordinate for the reaction on this coordinate plane here, this coordinate system. And what it tells us is that the energy starts at 100 kilojoules. So we're going to have a line here at 100. From there, the activation energy that's going to be required is 500 kilojoules of energy. So in other words, from here, we've got to go up 500 for our reaction to start. So what we're going to do is we're going to jump up then with our reaction and go up to this line. And then from here, it's going to have to go down to a point to where the difference between the ending energy and the starting energy is 200 kilojoules. Well, if we started at 100, then 200 kilojoules of energy based on the 100 is going to be down to that line, right? So we'll go down to here, and then our graph levels out like that. And you can see because this line here is higher than this line here, then the change in H, which is this number minus this number, is going to be positive, just like it is in our value here. So we'll just double check everything. We start off at 100. That's correct. We have an activation energy of 500, which is going to be 600 minus 100, this distance here. That's correct. And then the change in H is 200, and the change in H is the starting energy, the ending energy minus the starting energy. So it's this value here. And we look at that, and sure enough, that value is 300 minus 100, and it's 200 kilojoules. So that's our energy diagram. And the only other thing I would ask you here is that, is this a diagram for an exothermic or an endothermic reaction? And the answer would be endothermic. We actually didn't even need our diagram for that. You should be able to recognize it from a diagram, but because they explicitly gave us the change in H, and we know that it's positive, then we know that this is an endothermic reaction. So that's it for today. Let me know if you guys have any questions, and Lord willing, I'll see you on the next series of videos.